Okay, so we finished the last video talking about Taylor's theorem and the remainder and how we actually get the remainder, which I wrote out right here. And I said I wanted to work through one example of how we actually find this remainder, or at least how we get a bound on the remainder. So for this, we're going to use f of x equals ln of x. On the interval, we'll say negative 0.8 to 1.2. Because I know it's defined at 1, so we'll be fine there. And, well, let's see. First, I'm going to find the polynomial, because then I want to find the error on my polynomial. And in order to make this not too challenging, I'm just going to find the second degree polynomial. We did this in an earlier video. So really quickly, f prime of x is equal to 1 over x. F double prime of x is equal to negative 1 over x squared. And then let's see. If I write out my polynomial then, it becomes f of my center. We said I'm going to center this one at 1. So that's f of 1 plus f prime of 1 times x minus 1 all over 1 factorial, which is 1, plus f double prime of 1 x minus 1 squared all over 2 factorial, which is 2. Which, if I then plug in, gives me f of 1. When I plug in 1, I get ln of 1, which is 0, plus f prime of 1, that's 1 over 1, which is 1, times x minus 1 over 1, which is just x minus 1, plus, when I take the second derivative, I get negative 1 over 1 squared, so that's negative 1 times x minus 1 squared all over 2. And there's my nice second degree polynomial right there. So now I'm just going to give us more room. I'm going to erase all this. And I get x minus 1 minus x minus 1 squared over 2. So hopefully I can remember that. And I got x minus 1 minus x minus 1 squared all over 2. And for the sake of argument, cat, go away. Okay? For the sake of argument, I wanted to use, we said we were going to do this on the interval 0.8 to 1.2. So for the sake of argument, suppose I wanted to approximate it at 1.2. Well, then I would plug in 1.2, and I would get 1.2 minus 1, which is 0.2, minus 1.2 minus 1, which is 0.2 squared, which is 4 1/100ths, all over 2, which gives me 0.2. Let's see, the 100 goes to the bottom. That's 4 over 200, which is 2 over 100, which is 1 over 50, which is 0.2 minus 1/58 is 0.02. And I get 0.2 minus 0.02, that's 0.18. Okay, good. So that's the approximation my polynomial gave me for ln of x at 1.2. And I want to know how good that approximation is. So I have to find this remainder here. So the first thing I do is find the third derivative, because I found the second derivative here. Sadly, I already erased them, but I think we all know this. The third derivative is negative 2, it should be positive 2, over x cubed. Now, I want to find that on the interval 0.8 to 1.2, and I need n to be greater than or equal to every value of that derivative on that interval. So let's see, 2 over x cubed, as x gets bigger, the cube gets bigger, which means this gets smaller. So it will reach its maximum at the leftmost endpoint, because at the leftmost endpoint, x cubed is at its smallest. My leftmost endpoint is 0.8. So now, we did something similar with the Simpsons rule and trapezoidal rule, so this isn't a big deal. The maximum occurs at the left-hand endpoint, so that's 2 all over 0.8, which is 8/10 cubed, good lord, which is 2 over 8 cubed, which is 512, all over 10 cubed, which is 1,000. So it's 2,000 over 512, which is 1,000 over 256, which is 500 over 128. Good Lord, which is 250 all over 64, which is 125 over 32. And there we go. And those of you with calculators can do that much faster. 125 over 32. That's the maximum value of this derivative on that interval. So that's the value I'll use for my m. So then my remainder, r sub n of x, is less than or equal to m, which is 125 over 32, over k plus 1. Our original polynomial was second degree, so k is 2, so that becomes 2 plus 1, 3 factorial, which is 6, times x minus a, or the absolute value of x minus a to the k plus 1, which is 3. And now this is just the biggest this value can be, but it's actually just the biggest value of this interval from the center. So in this case, the distance is 2. If a is the center, any x in this interval at most is a distance not to 0.2 away. So I can say that to make this as big as possible, that's 0.2. Half of that interval right there. So now I simplify all this out. That's 125. 6 times 32. Good Lord. 6 times 32, that's 180, 192. 0.2 cubed, that is 2 times 2 times 2, 8 over 10 times 10 times 10, that's 1,000. And there we go. And then I can simplify that. 125 goes into 1,000 8 times. The 8's cancel, and this is actually 1 over 192. And there we go. And now I know my remainder is less than or equal to that. Those of you with calculators, if you want to check this to make sure we actually did all the math out, this is the value my polynomial gave me for ln of, we did 1.2. So that's the value of ln of 1.2 that the polynomial gave us. And the value, the actual value, should be within 0.18 plus or minus 1 over 192. And no, I have no idea what the decimal of that is. So then if you want to check it, plug ln of 1.2 into your calculator, see what you get, and then see if it's within this range, 0.18 plus or minus 1 over 192. It should be, assuming I actually did all the math out here correctly. Feel free to call or text me if I somehow did it wrong because I didn't have access to a calculator. But then, the idea of how this works is we would then say, this is my error right here. I know my error is less than or equal to that. So if that's within the tolerance that I wanted, then I'd say, okay, good, then I'm good to go because my remainder is less than that. If this is not strong enough, then I would take my polynomial and I would get the third degree polynomial. Then I would do this again and I would find the fourth derivative, find a new m, find a new value here, and get a new remainder, and I would keep on going until I got this remainder within the limits that I actually wanted. I hope that makes sense. I'm aware this can kind of be somewhat long and tedious and cumbersome, but it is actually really important. Understanding what this Taylor's idea right here, Taylor's theorem, says about taking a function and writing it as a series, but then approximating it with a polynomial and being able to bound your error is really, really important, because all of you know from an engineering perspective in the real world, when you have to solve these problems out, you're going to have to approximate things, and you have to understand how to correctly calculate the error, which is kind of why we go through all of this.